Good morning. My name is Ilaria Vitali. I'm working as Senior Research in R&D Unit for INTECS Solutions Company. INTECS has a consolidated experience in the development of software and hardware components, as well as solutions in all security-critical domains for the aerospace, defense, transport, telecommunication intelligence system markets in collaboration with the major European and Italian industries, university and research centers. In recent years, there has been a growing industrial interest in model-based safety analysis and its applications. These assessment techniques are based on a single safety model of the system and allow a high degree of automation, thus reducing the most tedious and error-prone activities that today are performed manually. An important feature of some existing approaches to the model-based safety analysis is the ability to automatically inject faulty behavior into a model based on fault specification for creating the so-called extended model. The failure logic analysis technique presented in this work aims at the automated calculation of the behavior in case of failure of a system from the failure behavior of its individual components. To this end, a semantics of failure propagation transformation calculus is outlined. The potential of automatic analysis is enormous. If the behavior of the system as a whole is calculated purely from the composition of its parts, then the impact of a component of architectural change can be predicted very cheaply. Furthermore, if unexpected failure behavior emerges at the system level of the model, it will be possible to quickly trace where its causes lie. Finally, it can be possible to identify easier where fault accommodation patterns must be added to the architecture to mitigate or correct potential failures. The failure logic analysis also supports the safety evolution process with the generation of artifacts typical and necessary for the certification of safety critical systems, the failure mode effect analysis table, and the fault tree analysis. The CHESS toolset provides a model-driven and component-based methodology for the development of high-integrity systems for different domains and contains a set of plugins integrated with Eclipse. The toolset implements UML, SysML, profile, a specialization of the modeling and analysis of real-time and embedded system profile, by producing extensions to Papyrus UML graphical editor for design views. CHESS supports model-based analysis of the systems for schedulability and dependability, as well as code generation from model. In particular, CHESS implements the failure propagation analysis and allows users to use the failure propagation transformation calculus technique for automatic calculation of failure behavior of entire system from its building components. CHESS implements also iterative development process in which a system model is updated every time. Its analysis results are backpropagated in the model and can be used for others' analysis. In the project, it is planned to improve the failure mode effect and failure tree analysis generation in the CHESS toolset to help identifying and evaluating potential failure modes, their causes and impacts, so well as identifying actions to reduce or eliminate those potential failures. In addition, it will be also provide to support agribot and health neuromuscular transmission use cases implementations for what regards the proposed methods and tools. In particular, these scenarios will be analyzed using chess for the creation of the extended models able to cover the risk analysis proposed for each use case under examination. It will be studied the rules necessary for the failure logic analysis, and they will be added on the use case models in order to describe the malfunction and their possible propagation. The automatic analysis will have the aim of early failures identification for injection tests. Thank you very much for your attention.